Hello everyone. In the previous chapters, specifically from chapter 10 to chapter 14, we covered all different types of solidification processes, which is under the umbrella of shaping processes. In this chapter, chapter 15, and the next chapter 16, we are focusing on the particulate processing, which is another type of shaping processes. So both the particulate processing and the solidification processing are under the umbrella of the shaping processing. Now, in this part of the book, we will focus on the processing of metals and ceramics that are in the form of powders. When we say powders, we mean very small particulate solids. Now, in case of a traditional ceramics, the powders are produced by crushing and grinding common materials that are found in nature. But in case of metals and in new ceramics, the powders are produced by a variety of industrial processes. Chapter 15, which we will cover today, is about the powder metallurgy. What metallurgy means? It is type or part of technology, part of science that concern of metal properties, characteristics, and production. So chapter 15 is about the metals. Chapter 16, or the powder metallurgy to be more specific, chapter 16 is about the particulate processing of ceramic and cement. Ceramic and cement. We will cover topics like what is the characteristics of the engineering powders, the production of the metallic powders, the conventional of pressing and sintering, and what is the alternative technologies. Now we will also cover the economic side of a view and the design considerations. Powder metallurgy. Metal processing technology in which parts are produced from metallic powder. So again, the parts produced from metallic powders. In the usual powder metallurgy production sequence, the powders are compressed into the desired shape and then heated to cause bonding of the particle into a hard, rich mass. Now, compression, called pressing. So we say pressing is a type of compression. We are applying pressure. That type of pressure is compression pressure. And that pressing is accomplished in a press type machine using tools that designed specifically for the part to be manufactured. The tooling, which is typically consists of a die and one or more punches, can be expensive. Therefore, must appropriate the PM is must appropriate for medium and high production. Since we have the tools, we can overcome the cost of the tools by high production rate or at least medium production rate. The heating treatment called sintering, which is performed at a temperature below the melting point, and that is the main difference between the particulate processing, and the solidification processing. Here we are working with a temperature that is below the melting point. Okay. Considerations that make the powder metallurgy an important commercial technology include the first important property of the powder metallurgy, that it can be mass-produced to net shape or near net shape, and that would eliminate or reduce the need of the subsequent processing. We only will need one or few processes to get the desired shape. Also, the PM process itself involves very little waste of material, so about 97% of the starting powders are converted to products. If you compare that with the casting process, for example, and the waste that occur in casting, especially with the riser, consider waste, the runner is a waste. You can see how much we will save material when using the powder metallurgy. Owing to the nature of the starting material in the powder metallurgy, parts having a specified level of porosity that can be made. This feature lends itself to the production of porous metal parts, such as filters and the oil in bearings and gears. Certain metals that are difficult to fabricate by other methods can be shaped by the powder metallurgy. This is another advantage, and we not forget to mention that certain metal alloy combinations and cermets can be formed by the PM that cannot be produced by other methods. However, that type of processes have some limitations and disadvantages. The first one is the cost of the tooling and equipment. Also, the metallic powders are expensive. Now, we have also some problems in storing and handling the powders. Limitations on part geometry, because the metal powders do not readily flow in the die during the pressing, since it's a powder, and the variations in density throughout part may be a problem, especially for complex geometries. These are some examples of parts that made using powder metallurgy. So you can see variety of products, size and shapes that made out of powder. And here we not forget to remind you that that type of a processing, we apply pressure and heat, but that heat is under the melt temperature. Now, what is the characteristics of engineering powders? Powders in general can be defined as the finely divided particulate solids. Most of the following discussion on powder characterization also apply to ceramic powders when we talk in the next chapter about the ceramic powders. In terms of the geometric features, the geometry of the individual powders can be defined by the following attributes. So first, the particle size and distribution, then the particle shape and internal structure, and last thing is the surface area. So how to measure the particle size? Most common method is to use the screens of different mesh sizes. The mesh count refers to the number of opening per linear millimeter or inch of screen. So when we have higher mesh count, that means we have a smaller particle size. This is an example of a screen mesh. You can see here that some of the particle will be small enough to pass through, while other particles would not be small enough and it will not pass through the mesh. Here is some terms to calculate the size, but you're not required to do these calculations. Now this is different shapes of the particles. Could be rounded, spherical, cylindrical, and as you can see, all of these different types. We see how we can have different sizes of particles and different shapes as well. One of the other features that we concerned of is the friction. And here I mean the interparticle friction, which is the friction that occurs between the particles itself, and that friction will affect the ability of powder to flow readily and pack tightly. One of the measurements that we look at is the angle of repose, which is this angle here. And it's formed by a pile of powder as they are poured from a narrow funnel, as you can see in this picture here. That angle could be large or small. Now, larger angles indicate that we have greater friction between the particles, and the smaller particle sizes generally show greater friction. So when we have smaller particle sizes, we have a greater friction, which means we can have larger angle of repose. The spherical shape results in the lowest friction between the particles. So now we can also notice that the shape of the particles is matter. The spherical shape is only have a smaller friction compared to the other shapes. When the shapes is different than the spherical, and the more it's differ from the spherical shape, the more friction we have between the particles. Packing characteristics depend on two types of density measurement. The first one is the true density, which is the density of the true volume of the material, and we measure that type of density when the powder is melted into a solid mass. The other type of density is measured when the powder is in the loose state after pouring. We notice that the bulk density is always less than the true density, because in the case of loose state of powders, we have pores, which is the empty spaces between the particles, which make the density less than the true density.